In this video, we are going to discuss about the power BJT, power MOSFET and DMOS. So first let us see about the power BJT. So here, bipolar junction, we know that bipolar junction transistor is a 3-terminal, 3-layer, 2-junction semiconductor device which is also having the terminals as emitter, base and collector. So we know the symbol is BJT, collector, base, emitter. The current arrow direction will be pointing from the base to the emitter in the case of the NPN, and in the case of the PNP you can see it is current is flowing from the emitter to the base. So here in this you have the structure, that is construction of the power transistor is entirely different from the signal transistor. That is, this power BJT is having 4-layer structure of alternating P and N type doping, and it has the 3 terminals which is labeled as collector, base and emitter. In most of the power electronic applications, this power transistor works in common emitter configuration. That is, the base is the input terminal, collector is the output terminal and emitter is the common between the input and the output. In power switches, NPN transistors are most widely used than PNP transistors, and the thickness of the drift region determines the breakdown voltage of the power transistor. Also, the characteristics of this device is completely determined by the how much amount of the doping is formed in both the layers and also based on the thickness. So this is the structure of the power BJT. Here the base thicknesses of each collector, emitter and base terminals are given, and the characteristics of the power BJT is entirely different from the signal level transistor. That is, first one is there is a breakdown, and it is available only in the case of the signal transistor, and the region which is lightly doped collector region is present only in the power BJT. The primary breakdown is the avalanche breakdown, and the operation of the device of the primary and the secondary breakdown region should be always be avoided because it leads to the catastrophic failure of the device. So you can see the power MOSFET. Here also you have the gate, source and drain, and another one terminal, that is TAB, drain. So the metal oxide semiconductor field effect transistor, that is MOSFET, is developed by combining the areas of both this field effect concept and MOS technology. So here it consumes more power, and also in high power applications these devices are used. So power MOSFET is a 3-terminal device, gate, drain and source, and this is the majority carrier device. As this devices is having high bandwidth and switching times, it is can be electrically isolated from the source, and it can be used in the high input impedance, which we also called as it acts as a good capacitor. And this is a self-protective device. Also it has no on resistance, and no junction voltage is produced when it is a forward biased, and it produces an extremely attractive power supply switching device. A symbol of this power MOSFET is given here. So you can please see the symbol. It is arrow is pointing inwards, and the direction of the current is flowing to the body of the region. Can you see the structure of the power MOSFET here? So this power MOSFET is actually having vertically 4-layer structures which has the alternating of P and N type layers. This P type middle layer is called the body of MOSFET, and also the N layer is called the drift region. The gate terminus is isolated completely from the body by silicon dioxide layer. When the positive gate voltage is applied with respect to the source, this N-type channel is formed between the source to the drain. So to avoid this BJT, P-type body region is completely stored in the source region by overlapping the source metallization onto the P-type body. You can see the characteristics of the N-channel enhancement mode. So based on the voltage variation, there will be a saturation region, cutoff region and active region. And this one is the double diffused DMOS. So diffused channel MOS structure you can see in the case of the drain, source and gate. Here you can see the length, channel length L. The channel length is of smaller distance, and also when you are applying the voltage, it causes the inversion in the substrate of and the n-type regions will be causing the inversion layer, which is completely acting as a conducting channel which flows the currents to flow from source to the drain. Thank you.